And we're going to continue this trip into the material world with a presentation by Julian Oliver. He mentioned that he won a Golden Nika that he's brought to us by the Goethe Institute, and that he will give a talk tomorrow night at the Goethe Institute on transparency. He'll give a workshop on Friday, and he'll give an ATC lecture on Monday. So we have a full Julian Oliver weekend coming up, and we're really excited to have you here. Please, let's see, what else can I mention about him? His art career, he's an artist, and he practices the critical practice, something we do in this building as well, downstairs in the Invention Lab. And his critical practice has taken him all the way to the stratosphere, because he has launched balloons that scan the transmissions between Earth and satellites. So his critical practice has taken him into many unusual spaces. And here we go. Please welcome Julian Oliver.
Thank you very much. Thank you very much, guys. Hi. Good. So I'm going to try and keep this within the half an hour that was allocated to me. I guess that's going to take things a little bit swinging toward the lunch side of things, which is a bit, well, the late lunch side of things, which is a bit rough, but bear with me. I'm just going to sort of rip through it. I speak with a New Zealand accent, which is not an Australian accent. It's a New Zealand accent. New Zealand is 4 hours by plane away from Australia. I just took that flight again. I live in Berlin, so I might also occasionally drop occasional German word in there every now and again. But if you find it too much of a struggle, we can always catch up immediately after my talk, and you can ask me a few questions there. Now, initially, I decided to call this talk Point, Line, Node, and Route. I really want to look at the topological and material extents and delimitations of computer networks, and how they ascribe or even prescribe transparency and our interaction with systems and automated and integrated systems. However, without knowing much at all as to how networks work, we are somewhat withheld from being able to meaningfully and critically engage them, especially within conversations like the topic of this one-day conference. I actually last night, in the grips of a 23-hour jet lag, after a 22-hour flight, I decided to change my talk to this, manufacturing opacity, just to be a little bit provocative. I'll start with a Bruno Latour quote that I think is a very important one here in that frame. When a machine runs efficiently, when a matter of fact is settled, one need focus only on its inputs and outputs and not on its internal complexity. Thus, paradoxically, the more that science and technology succeed, the more opaque and obscure they become. Bruno Latour was really important for a vast variety of things, actor network theory among them, but he did popularize, at least within critical theory, this concept of the black box. And what he added to it was a very necessary discussion about the black box in the context of control. So it wasn't just necessarily that the black box was opaque, but that there was a feedback control loop that the manufacturer, or at least the system administrator of that black box, the owner of it even, has access to. So while the so-called user, in fact the only people that talk about users are really drug dealers and interface designers. But yes, let's just call it that person, the user, engages with the black box on the basis of inputs and outputs. And they might, for instance, apply input to that box and get the expected output from it, ideally. There may internally be a feedback control loop, a backdoor, you could even call it that, that has nothing at all to do with the user's expectations of that flow. Take the subject as an example. This was the hot MP3 player of its day, the gramophone, and I like to think of this as a very transparent and a very outward-facing object. In fact, you could argue it's a very socially engaged object in that its inner workings are expressed outwardly. We can see that if we turn this handle here, our energy input, if you like, our energy source, which is in this case kinetic energy, results in this platter here turning. And if we look very closely, we can see that that record has a little needle on it that bobs up and down as the record turns, moving in a spiral formation toward the center of that record. And all the while, outside of this large horn, we can hear sound. And that sound is expressed via an amplification that is described by the very form of that horn. Compare that, for instance, to this object, which is a iPod Nano. None of its inner workings are expressed outwardly. In fact, it's just a field of surfaces, of metaphors that ultimately abstract over inner functions. In fact, almost no one you or I know would be able to tell you precisely how an iPod Nano works. They wouldn't necessarily, on opening it up, see where the energy interface is on this object, where the songs are stored, like where is the record equivalent. They would not know necessarily where the fast forward or skip, I should say, skip back and skip forward events actually occur. And there would be a wall of lawyers, or might I say, for the collective noun, a murder of lawyers between you and doing that. You'd actually depreciate the value of that object that you supposedly own in the course of trying to inspect its inner workings. So we have opacities of complexity and scale. And our domains of action are no longer discrete when we have abstractions over inner functionality at the metaphorical and symbolic layer. So you can think of seamlessness as kind of design hiding engineering. And I often like to refer to this, again, provocatively, as an ideology of seamlessness. That itself engenders an expectation of seamlessness, of that as I project, almost phenomenologically, as I project a desire to act, the technology should follow. And I should be left with nothing else in the foreground of that process. There's no better metaphor for all of that than the cloud, which is a highly patronizing image, one could argue, in that it entirely deterritorializes and dephysicalizes, transubstantiates the very material reality of what it is to use computer networks today, particularly on the large scale of a wide area network. Now, the cloud has no territory. It belongs to no country. It, in fact, changes form. It comes and goes. Clouds belong to the world. We would like to think. So when someone says they're just going to push data up into the cloud, and then, as I heard one guy say, coming into San Francisco airport, but a long time ago, I left, I think it was Amsterdam, with him, and he said he's going to push it up, and then he says, when I bounce down into San Fran, I'm going to suck it down. Like his idea is he's going to push the data up, and for some reason he needed to do that before he flew, and then land in San Francisco, and then pull the data back down from the cloud. And his hands were moving up and down as he was gesturing. It always struck me as a very odd thing, really. And I later read that same year that unfortunately almost 50% of Americans done in a rather large survey believe that cloud computing is affected by bad weather, which is rather worrying. It's not to say that those people are at all idiots. It is to say that there has been no groundwork done to educate them as to precisely what this cloud computing thing is. And that is a very privileged position to be in, should one be a cloud services provider. It's a readily exploitable ignorance. The field of surfaces that we do work with also occur in a screen framing, and they often take this form. But without edges and seams, we cannot locate ourselves. We don't know where we stand, you could say. Here's an image of a girl that's just run across a street that I traverse often in Berlin. She's just run across the street from East Berlin into the west, and the cops are having a standoff. She's just escaped. I love that image. So one can ask a child, for instance, as to the basic functioning of the solar system or how a flower works, but you can ask very few people and they can coherently answer for reasons that are not their own fault necessarily. What is a computer network and what is the internet? Here is an actual topological rendering of the internet done some years ago. Where am I on the internet? I mean, who can say that, for instance? who can answer that, I should say. You are here. There is a sense of placefulness. And so when we're talking about topologies and graphs, we're talking about a layer of abstraction that can, interestingly enough, give us an insight into where we stand and where the opacity actually occurs in a network context. Topologies began with really Euler, who solved this the 7 bridges of Königsberg problem, which was a network of bridges in Prussia. The question was: is it possible to traverse all of those 4 regions, crossing each bridge only once? And he negatively solved it in that he said it was not possible, and inadvertently invented topology, which basically became ultimately our graph theory. And here is a topological representation of the topographical problem. So you can see you've got these 4 regions become blue dots, and the bridges become these black lines. That's an important sort of conceptual abstraction to be able to reach when understanding computer networks as topologies. We have concepts of betweenness. Here, for instance, is a topological representation of a social network, where going from red to bluest blue, those red dots have the least betweenness, and therefore have the most redundancy within the network, compared to, for instance, this blue here that has the most betweenness. The most other nodes depend on that blue or are connected to that blue. So we have this concept of centers, both local and global. This blue has a high local centricity or centrality, and also a very, very high global centrality, whereas these red dots have almost no local or global centrality. So centers are implied by connections, and that's important here. Network topologies and the stack. I'm just going to move quickly into the stack representation here. We have the application layer at the very, very top. That's our browsers. Programs like Skype, etc., any application that ultimately interacts with a network service. And right down the bottom we have the physical layer. And I'm just going to quickly walk through the bottom 3 in relation to the top. So the physical layer, we have the layer of the materiality, the stuff of the network. This is Ethernet cables, switches, routers, etc. Here is an early representation of the physical layer of the telecommunications, the phone network in Stockholm. Like here, going over the city, you could actually trace a line from a home to another exchange and then onto a home. It was transparent in that the infrastructure was lifted up over the city rather than buried under the ground. I love that image very, very much. Here, however, we have today cell towers, which could not be more blank or more opaque. The only thing they tell us is the direction that they're pointing in. There's about 12 base stations on that cell tower there, each of which is using a directional antenna. We have the submarine cable map here, which was a very, very important project in that it shows us that very little of the primary geophysical, if you like, network infrastructure is in fact publicly owned. You hear a lot, unfortunately, you hear a lot in conferences on technopolitics. You'll hear humanities people talking about the internet belonging to the people and it must be returned to the people. In fact, by looking at the submarinecablemap.com site, you will quickly find that the internet has never belonged to the people. The closest you'll get to public space is pretty much like the fountain or meet and greet point in a shopping mall. But I mean, you click on these lines and you find multi-billion-dollar companies quite often in control of those cables. Every now and again, you see that there is a government in control. She or he that controls the route controls the content. Here is a submarine cable cut in half. A friend of mine, Trevor Paglin, is doing some wonderful work on submarine cables right now, going underwater and taking photographs of them. Here is a shark attacking a submarine cable. People don't yet know quite why sharks have started attacking submarine cables. Some people say that they emanate a sort of a sonic or acoustic fingerprint that resembles a fish dying. I love the shark's putting a bit of muscle into it there, getting a bit of kick into it. The data link layer. The data link layer occurs, like for instance, with an Ethernet cable where you plug it into your laptop and you see a link light come on. That means that electrical signatures have been moved across the cable infrastructure or the physical layer and are recognized by the network interface controllers at the endpoints, and you get a link. That is in a wireless and wired context. That is done using these things called MAC addresses, hardware MAC address. These are unique signatures, unique fingerprints. You can stand outside someone's home, I'll show you a little bit later, and tell whether they're home. You can call them and say, "Are you home?" And they'll say, "No, I'm not home." But you can see that their phone is emanating this address. I'll show you a bit about that later. Here is a link done at the link layer with these unique hardware fingerprints. And onto the network layer, we need to understand these different layers in order to understand topologies and how they impact us and how we can impact them. IPv4 space, the Internet Protocol version 4, operates 4.3 billion addressable hosts, network hosts, or you might think of them as nodes. The Internet officially ran out of numbers in 2011, and so we needed to move to IPv6, which is a process taking a long time to come underway, to be rolled out entirely. The idea is that every human will have 1,000 or so unique addresses. Their shoes can be addressed, their child can be addressed, their dog or dogs or iguana can be addressed. I'm in California, so I'm sure there's iguanas as pets here. Probably is. I don't doubt it. And we see that IP addresses, which are these flexible numbers, these four blocks of numbers, change in relationship to the MAC addresses, which are static. So as you go from a home to a cafe, onto a library or something like this, or an airport, your IP address will change, but your MAC address will remain static. And routes describe centers. So when we start looking at topologies, and they occur at many different layers, both the physical layer, like the submarine cable, that's very much a topology. You see actual cables across the surface of the sphere that we're currently on represent a topology on the physical layer. On the link layer, as you'll see a bit later, you'll see that topologies can be described by the links between devices, regardless of the cabling that they're actually using. Regardless of the physical layer. There's ways of them operating relatively discretely from each other. And then on layer 3, on the network layer, however, is really where we describe topological relationships and networks. Now, a ring network here would require that, say, if this node here wanted to communicate with this node would need to talk through these two other nodes. Here on a star network, which is your network at home, it's a small office, home office network, for instance. All members must go through the central node, which will be your router, and the router is the thing that connects you to the internet. So all traffic needs to pass through the center. On a fully connected network, which is more of a hypothetical network, everyone can talk to everyone else. So that's the most transparent and the most open, and it's also the most ridiculous. It's completely inefficient. But it's often used in military applications because it's really built for redundancy. On a line network, you can imagine that if this one here wants to talk to this node here, this node's got to talk through all these other nodes. On a tree network and a bus network, we see similar problems. The mesh network is very interesting, but I'll address that later. The important thing to understand is that network topologies are inherently political. They describe states of political control or loss thereof. IPv4 also expresses territories, which is quite important to understand. We have local area network addresses, for instance, like the network you have at home, and these are designated address spaces that are only for use on local area networks, home, office, or whatever. The internet is a whole other class of addresses. So we have this idea of interiority and exteriority with the IP version 4 that we all use all the time. Inside and outside. MAC addresses, these unique signatures, do not actually traverse the threshold between inside and outside. Network address translation, or NAT, expresses the possibility for the internet, when it ran out of numbers in 2011, to continue growing. Here we see a 10.3.2.1, let's just say that's a local area network address. communicating with an internet address at 89.262.6771. That's an upload action from a LAN to a WAN. And then the download action coming from that same external WAN, a wide area network address, back to the LAN. Here we see that represented in a Kaida walrus graph, a beautiful project. You can see here that this dot in the middle would be the router. Because what a router does is a router connects any two networks together. That's all a router does. It's a device for connecting networks. And we see this tree of stars phenomenon with lots and lots of blooms of centers, each of which might be a university department. I think this is actually a university. So you've got different departments in a university. And these little endpoints here might just be phones, smartphones, laptops, terminal endpoints. And so we have these clusters and trees of stars, if you like. These wheels, these hub and spokes, as they're often referred to. But we have expressions of control all the way along the route. But the router itself, the main router in the building, is the site of most political control. Another representation there. I think it's a military network. So tracing the route, let's just pop over to a browser right now. So let's just have a look at this now. Well, you guys just click on something. But I wanted to know exactly which name server I'm using. So let's just go to my studio's server. We actually have our server in our studio in Berlin. I'm just going to do a proxy trace here. Look at the different number of hosts that pop through here. This is seconds elapsed. It's doing the trace at the moment. I like this because it shows the actual geographical reality of it all. It takes a while. Come on. Ah, that's too long. I'll go for another domain. What's another domain? I'll go for spiegel.de. Oh, I'll cancel that trace. Okay, cool. Proxy trace. Cool. Or have I been pumped off again? Don't do it to me. No, I haven't. Didn't take that long last time. Oh, I'll do google.com because it's closer. Don't know why it's taking so long now. I know why. I can't do it. The guys here are blocking ISMP packets. Can't do it. Anyway, forget it. I'll just get on with the talk because we're running out of time. Anyway, when you visit google.com, Facebook, or whatever, your packets are copied across routers as a copying action. You never visit a website. You ask a website to visit you. You never visit a website unless, of course, you're say you want to visit the BBC and you work at the BBC. You physically go down into the data center for the BBC and sit there and plug your laptop into a machine and physically copy the website off onto your machine. What happens is you request a website and it is copied across network hosts, often up to 20 network hosts, quite commonly between you and the data you're requesting. You actually receive a website from the router in your room. Here is a wireless router, for instance. Importantly, network service centralization is the practice of maldistributing topological control under the science of efficiency and convenience. And I want to talk about centralization in the context of the internet. Let's look at a man-in-the-middle attack here as a metaphor. The internet was never designed. I mean, it began as an attempt for networks to connect to each other. So there was networks reaching for each other in order to communicate. In fact, it began in an inherently decentralized, or at least uncentered state. The recentering that's occurring is strictly grouped around services and service use. Let's just look at man-in-the-middle attack as a metaphor for thinking about, for instance, service centralization in the context of data centers, Google, Facebook, and the like. As I said earlier, she, he that controls the center controls both route and content. I'm just going to quickly present the project News Tweak, which uses the 3 different layers of the physical layer, the link layer, and the network layer to literally turn a wireless network into a kind of reality island. And you'll understand the project a bit more, I suppose, with the video. But it comes in the form of the most mundane-looking object one could possibly imagine. Curators are very frustrated when we present this because it's designed to be completely uninteresting, unnoticeable. It could be, for instance, a barometer plugged into the wall, or it could be a sensor in a building of some sort. It looks like an object of utility. You plug this in, and the owner of it can then fly to Kuala Lumpur, Auckland, New Zealand, San Francisco, and then from the comfort of their mum's place or a 2-star hotel, they can manipulate the news read on that wireless network. So you can change sporting results, election results, etc., etc. It attacks the local wireless network, routes all of the traffic through itself, and provides a route for the owner of that box, wherever they are on the internet, to be able to manipulate the news. And it does so by changing the relationship between IP addresses and those MAC addresses I was talking about earlier. It's a classic man-in-the-middle attack, but done in the form of a small little plug. And you see results like this. This was from an exhibition in Brighton where we set up an office where people could walk into the office, which was like a newsroom, and actually just manipulate the news on a network somewhere else. So people were taking screen grabs, and we show this piece a lot. And you see a lot of this sort of thing. I will squeeze all the oranges is really one of my favourite. He has indeed squeezed all the oranges in the UK, that man. Friends, don't let friends drink and cuddle, which is really a really good idea, I think. Yep, no worries. So quickly, I can't show you the video because the sound doesn't work here. The internet itself was not designed, as I said earlier. Here is ARPANET. What has happened is there's an optimization logic, a dominant and almost of a sort of an ideological scale to optimize the internet around services. And obviously we love optimization. I mean, I work a lot I do a lot of engineering, and I spend a lot of time optimizing. And I see something like this, and my engineer brain reaches forward and says, just cut a road over that hill. But the part of me that also grew up in the countryside and does a lot of hiking and trekking says, no, don't, leave it, and see more of the hill by moving through it. And centralisation often masquerades as optimization, when in fact it does quite the inverse. And there is no better example, I think, than the centralised traffic hub example that I saw in the wonderful book Seeing Like a State by James Scott. When we centralise, for instance, a traffic hub like this, we're actually doing away with the possibility for a shorter traversal from, say, these points A to B. One has to go through the centre, and this is precisely what's happened with Moscow. The city plan is such that everyone must route through the centre to get to any other location. So it's an administrative kind of a capture through the network topology itself. Le Corbusier's plan for a monocephalic Paris, where all of the administrative and higher functions of the city were centralised around these sort of core routing nodes in the middle, such that the rest of the city around would merely be for those farmed taxpayers, if you like, the good people of Paris. But in the middle, the higher functions were represented in this sort of centric model. And an example here we have of this sort of an opacity at the metaphorical layer over the topological imperatives that deeply define issues of transparency in a context of surveillance could not be better represented, I think, than say Dropbox and Google Drive versus BitTorrent. BitTorrent now, of course, is associated with this illegal file sharing, whereas archive.org and many Linux distributions use BitTorrent to laterally distribute files between peers in a very, very efficient manner. Dropbox, however, is a centric model, such that I'm at a workshop and I'll be sitting next to someone who will be wanting to share a file with their friend. They will upload it to Dropbox across 20 different machines at potentially a massive environmental cost. I mean, who knows what the carbon footprint of that transaction is? You know, fans speeding up, the temperature of the room getting a little bit warmer, perhaps, and then pulled all the way down over that route to the person to that person next to them, versus BitTorrent, which would look for near or topologically near peers in order to take chunks of that file from them to reduce the network load. So Dropbox would have the look of being a highly efficient or an optimization within the context of say, just simply sharing files, but in fact it is quite the inverse. It doesn't even leverage the network to do what it's best at doing, which is route redundancy. Here we have a minimum spanning tree optimization, which could, for instance, describe the way that Dropbox would like to work. Here, this is the minimum span to provide a route access to all the different other routes within this mesh. So I would say we ought to talk less about decentralized networks, because networks like mesh networks are not decentralized. They never were centered. We need to talk about centerless networks. I think that's just here's the fully connected in a mesh network there from earlier. And just 5 more minutes. That would be, yep, I think. We have the data center. Now, the data center is the maximum of absurdity, I suppose, in the context of an abuse, in many ways, of that route redundancy, of leveraging that route redundancy. Network centralization either expresses or is an expression of privatization. Here we have another. Of course, I just had to throw that in there in the context of this. This is Louis XIV being proposed by the Marquis de Vauban. He's proposing a census, and says, would it not be a great satisfaction to the king to know that at a design moment every year the number of his subjects in total and by region, with all the resources, wealth and poverty of each place, the number of his nobility and ecclesiastics of all kinds, of men of the robe, of Catholics and of those of other religion, all separated according to the place of their residence? Would it not be a useful and necessary pleasure for him to be able, in his own office, to review in an hour's time the present and past condition of a great realm of which he is the head, and be able himself to know with certitude in what consists his grandeur, his wealth, and his strengths? It's just Snowden advising against Dropbox. But it's talking of the data center, and at its most sinister respects, of course, there's probably no better image than this. This is from the Bureau of Statistics in Amsterdam. And it was I suppose, a gift to Hitler, denoting the regions most populous with those of a Jewish background in Amsterdam in 1941. And so we have the census expressed there. And I know that might seem a little bit coarse, but there are these network effects. And there's other network effects. In this case, it's NSA's Utah data center used 6.2 million gallons of water for cooling. That's another network effect, desertification. Centralization, optimization expresses itself in highly suboptimal representations and other ways there. And I'll talk about the transparency grenade tomorrow night at the opening, so I won't need to discuss it now. But I just will leave you with what I promised you earlier, in that, in any case, we can quite safely say that transparency almost has an energetic expression in that there's a leaky bucket problem, the leaky bucket problem of unintended emissions, whereby it doesn't really matter quite what you do. Let me just do it like this, actually. It doesn't really matter quite what you do, how much you'd like to end it. You'll always find that devices will speak behind the backs of their owners. In this case, here is all of the access points from view of my computer, and down here are your cell phones, iPads, laptop computers, and you will even see probe requests to networks you've been in the past. You'll see cafes you visited, your auntie's printer, a hotel you visited in Kuala Lumpur, or whatever. They will be there as it hops through the channels. And so despite the fact that we might have a closure, physical closure with our object, we might not be able to reach inside and even see its inner workings and understand how it works. We can definitely quite safely say that, that our objects are leaking regardless, and that opacity has many challenges there. I'll leave it there. Thanks very much, guys. Good. Enjoy lunch.